Hello, my name is John Shramsky. Thank you for attending this lecture. The title of my talk today is Energy, Design Theory, and the Future of Technology. And this work represents a manuscript that's in process by myself, Jasmine Batty, and Trey Richards, all of us together here at the University of Georgia. I have 12 slides today, and I've numbered them down here in the lower right-hand corner, so you can keep an eye on that to keep track of my progress. If any of the concepts that we talk about here over the next 13, 14 minutes are of interest to you, and prior to us getting our manuscript out, there's two journal papers that have been recently published that if you take a look at those, they're shades of some of the materials that we present here that are also in these journal articles. But also, perhaps most importantly, I also have a lecture next week at the 4th International Conference on Energy Research and Technology. This presentation is a keynote, so it affords me 45 to 50 minutes plus a Q&A. So it'll give me more opportunity to expand on the concepts presented here by quantifying them, adding some case studies and whatnot, providing further depth. So if that is of interest to you, please look into attending that conference as well. I'll also show this slide again at the end of my talk here so that this information is available to you. Okay, with that in mind, the topic of my presentation today is energy design theory and subsequently the future of technology. We'll begin this talk by talking through the concept of energy a little bit more in depth, and then ultimately leaving us with 2 points before we move on to discussing design theory. First, when I mention the word energy, the vocabulary word energy, it can actually conjure up multiple things depending on your background, your training, or your career. So let me take the first slide and just make sure that we're all on the same page. In the beginning, at the inception of our planet, the formation of our planet about 4.5 billion years ago, what I'm showing here on the left are the energy gradients that existed at that time. And then the evolutionary process took over, and we of course started with single cell organisms leading to multi-cell organisms, so prokaryotes leading to eukaryotes, and all of this eventually sort of ended with probably the most important period in the development of additional energy gradients, and that would be the Cambrian explosion, where the photosynthesizers overtook the planet and provide a systematic way to convert solar energy into chemical energy, making it available to the diverse species of life that continue to evolve on the planet. This ultimately led to the biomass consisting of phytomass and biomass of animal species and insects and whatnot, together comprising the biomass of the planet. And then over time, given sufficient 100, 200 million years, of course, that leads to the fossil fuels as we know them and as they're stored on the planet. And if all this is functioning properly, of course, then we have our hydrosphere, the condensation and evaporation of water, and our oceans and the currents and waves and tides in conjunction with the gravitational forces and whatnot that comprise the total system of energetics on the planet. So with this background, if I put this graph up, we are now all of maybe a relatively basic understanding of the energetics necessary to work in concert in order for the planet itself to act as I like to refer to as a rechargeable battery. So all of these energetics work in concert for the process of net primary production, which is the total accumulation of phytomass, converted energy from solar energy to the chemical energy of the phytomass and the biomass of the planet. And so we have a yearly introduction of phytomass to the planet, which then resides in the biomass and is either used and then ultimately stored over hundreds of millions of years, or is degraded into heat energy that leaves the planet some later time. So this is a very balanced and very choreographed system that was engineered, frankly, over 4.5 billion years, and really over the last 400 million years in particular. We present this so that we can then show the juxtaposition of the current energy consumption of humankind, which is represented here by the red graph, or the red line on the graph. This we're showing, let's see, 400 years on the horizontal axis, and then you can see the rapid rise particularly over the last 70, 80 years. We are currently discharging about 580 exajoules per year. This is an extremely large number, and which leads me to the first point I'm going to make without a lot of additional descriptions, because we don't have the time here, because I'm going to spend my time on the second point with regard to energy. But the first point is that this number, frankly, is just too big. You can kind of get an idea of how big it is just by the rapid ascent, and then how that would try to overlay in any kind of semblance of a sustainable way with the energetics of the planet that we're showing, visually over here on the left. In fact, I can just leave you with two quick numbers to give you an idea for your intellectual curiosity. But if we're discharging 580 exajoules per year, that works out to be about 17% of all of net primary production on the planet. So that would be all of the new growth of plant matter in both the oceans and terrestrial systems of the planet. And so that we're not burning 17% of that net primary production. It's just the fact that what we are burning represents in magnitude 17% of all of net primary production on the planet. Clearly, this is too big and not anything that can be balanced in any reasonable way from an energetic standpoint. And just as another number, this 580 exajoules works out to be 3% of the total global stored biomass in the oceans and terrestrial systems of the planet. Total global biomass is around 20,000 exajoules in total. Most of that, about 85%, is in forest, and what we are burning represents about 3% of that in total magnitude. So for these reasons and many others that but I think you can get a general idea where we're at. We'd like to leave it with the statement that humans are simply burning too much energy. This is important because the discussion of energy by humans is normally focused myopically on renewable versus non-renewable, clean energy. Is there going to be enough? And we clearly think that we are leaving probably the biggest discussion off the table for reasons that are unknown, I suppose, but that the bigger discussion needs to be that we're burning too much, and how does that affect the energetics of the planet? So the second point that we want to make is, I think, the more poignant and maybe the more important, and that is that if we consider energy is the ability to cause change, that's the definition of energy, right? And then if we discharge energy, then this causes change, right? And so with this in mind, it can be easily said from the laws of physics that energy discharge is a forcing function. And so what do we mean when we say change? If you discharge energy, you're going to move material, or you're going to alter the chemical composition of material, or you're going to change the temperature of the material, the molecular activity of the molecules themselves. Okay, this is a fact. And so what this means is that as humans discharge energy, it is reflective of the amount of change they are causing on the environment. So let's look at some empirical data on this regard. So here is our global primary power consumption curve, the red line. Okay, and then if we look at Stefan et al.'s age of acceleration figures, all right, the most recent being published in 2015. If you look at the human socioeconomic drivers, so this is a representation of human activities being fueled by the amount of energy being available, and it should be no surprise that human activities are rising at the same rate that energy discharge is rising. They're all, graphically speaking, exponential or near exponential graphs. So our water use, our paper production, telecommunications, fertilizer consumption, as we undertake these activities, we have unlimited amounts of energy, and our activities are increasing exponentially. This is the age of acceleration, and it's because we are discharging this energy and have this energy to discharge. It should come as no surprise then, the Earth biophysical reactions, the environmental reactions, are also exponential. So if you discharge an exponentially rising amount of energy, you can expect an exponentially rising environmental impact. The take-home point here is this: as long as we have an exponentially rising energy discharge function, we're going to have exponentially rising environmental reactions. We can expect no stabilization in these environmental parameters or any others that we match for that matter, as long as our energy discharge is also exponential. The only way these will stabilize or start to go down is when our measure of environmental change, our energy discharge, is also going to begin to go down. So with that in mind, that leads, humans are burning too much energy. Energy discharge is an exponential forcing function, generating exponential environmental change. And it can be said that no mechanical or environmental system can survive an exponentially rising forcing function forever. That's a fact. All right, so then that leads us to consider design theory. Modern design theory is to provide goods or services with increasing efficiency. We design the initial widget, device, or system with an intended bogey in mind, whether it be cost bogeys or natural resource limits. And then once that initial design is complete, we consider improving those designs by redesigning the device or the system in such a way that it has the same outcomes, provides the same services, but at the same time it uses less fuel, less water, less plastic, less money, etc. And so this is the crux of modern engineering design theory. You design it with the best efficiency available, and then you continue to improve it by further improving the efficiencies themselves. Unfortunately, we now know with 100% certainty that this has a total systems outcome that was somewhat foreseen, but now we have empirical data to show, and that's this. Improved efficiency of engineering designs results in increased rather than reduced energy and resource consumption. This is why we are now in the age of acceleration. And the reason for it is it's complex, but mainly for this. For this reason, these innovations allow the technologies to be more profitable with lower prices leading to increased demands. This was put forth by the economist Willie Stanley Jevons back in the mid-1800s, and he and is otherwise now known as Jevons paradox. Nevertheless, we now know this to be true, 100% true. And in fact, we can look at Stefan et al.'s data that I just showed you a second ago for empirical evidence of this being the case. As we improve efficiencies along the way in our overall design process, whether it be for sustainable reasons or cost reasons, those resources are not then returned to the earth for environmental stability. In fact, those resources are now made available for others to use. And then as others use those, this increases our environmental degradation and leads to the acceleration that you see here. So this is a fact. So if modern design theory is no longer applicable, then it is certainly not applicable in sustainability science. It's no longer acceptable to tell somebody redesign this and use less energy or use less wood, and then we can call that a successful sustainable design. The fact is that future engineering design theory must absolutely flatten the energy curve. So this curve must be flattened, and this must be the future of technology and the future of engineering design theory. And to the extent that's now available in current COVID-19 virus circumstances, many of the methods that we are using to flatten the infection rate of COVID-19 are similar to the activities in the mind and the mindset that we're going to have to consider to flatten our energy curve. We must start engineering our lives and engineering the human existence in such a way that we are doing less with less. This is the only way. We can't rely on improving efficiencies anymore. We must undertake activities and designs to which we flatten the energy curve that we're showing over here. I'll be able to expand on these, of course, in our manuscript, but also in the presentation that I mentioned that I'm fortunate to have next week with some numerical examples. I sincerely hope that these thoughts have been intellectually curious to you. And if you have any additional thoughts on these, please don't hesitate to email me, and I'd be glad to engage in that conversation. Thank you for your time. I'm glad you had the opportunity to attend.